Hello, everybody. Welcome to our lecture for Friday, March 10th, where we move on to our final bonding model. So we've so far looked at the Lewis model, the Vesper model, and also valence bond theory to explain the phenomena that's known as chemical bonding. And we've now arrived at our last discussion of chemical bonding, which is the one that is I guess you could say, not the best, but it best models what we see in the lab when we go and explore the bond strength, length, and molecular nature of different types of compounds. And this particular bonding model is known as molecular orbital theory. So let's start with a working definition of molecular orbital theory, which I'm going to refer to from this point forward as MO theory. So define MO theory. This is a bonding model that places covalently shared electrons throughout an entire molecule based on the formation of molecular orbitals. So what we have seen thus far is in valence bond theory, we said that a bond is some kind of atomic orbital overlap, where we have our half-full atomic orbitals overlapping to form a spin pair, and we had our head-on overlap, which gave us our sigma bonds. So a little sketch of that. So I'm going to look at our hybrid orbital. So here's our sp hybrid. And if I'm looking at the overlap of this with another sp hybrid in this head-on manner, then the spin pair, or the resulting bond here, forms a sigma bond. And if I were to look at some side-on overlap of atomic p orbitals, so these are like our unhybridized p orbitals left behind in sp2 and sp hybridization, this side-on combination creates something like this. So let me redraw these. So here's a side-on combination of p's. Where it is in this side-on overlap here where we can form a pi bond, which can be a double or triple bond, and it's always formed after or in addition to the formation of a sigma bond. And remember, like, what are these orbitals here? So this orbital is looking at our sp hybrids from or on the central atom. And this is looking at unhybridized p orbitals on the central atom. So in both cases, all of the orbitals involved in some kind of overlap, which we call a bond, come from the valence orbitals on each individual atom. How is this different from what we're going to see in molecular orbital theory? So in MO theory, it is not just our valent atomic orbitals that are responsible for creating these regions of overlap and housing our bonding electrons. In fact, what MO theory says is that all atomic orbitals, meaning both valence and core, interact to generate new orbitals that are dispersed across or over the entire molecule. And this is what we call molecular orbitals. So the difference here is that it's all atomic orbitals, not just the valence ones that we have to consider their interactions. So we're going to be looking at, for example, something like if I had, I don't know, let's see here. What if I had N2? No, let's do F2. So if I were to think about how this would be different from a molecule that's like constructed differently from valence bond theory compared to MO theory, let's look at our electron configuration for fluorine. So let's throw a periodic table up on the board. Okay, fluorine. I'm going to write the full electron configuration. That is 1s2, 2s2, 2p5. And in valence bond theory, we would only look at interactions that result from our valence. So this would be something like the 2s2 and 2p5 on each. So it's either these interactions or the hybrids of these atomic orbitals AO. Whereas in molecular orbital theory, we look at the interactions of every single atomic orbital. So this includes not just our valence orbitals of 2s and 2p, but also interactions of our core orbital 1s. Now these interactions are combinations in a similar way that we saw like combinations of the internal S and P on one atom creating our hybrid orbitals, right? Our sp hybrids. And let's call them hybrid orbitals. We're not talking about hybridization, we're talking about hybrid orbitals. And maybe that's a little confusing, so we're going to check. Now, the combinations that we're looking at in MO theory are what's known as linear combinations of our associated by energy level orbitals. So we're going to look at what happens when we have a 1s coming together with a 1s from one fluorine and another fluorine. Whereas in valence bond theory, we were looking at what only the valence orbitals were doing. So in our next video, we are going to consider what these linear combinations of atomic orbitals are and the resulting molecular orbitals that they form. And once we have an understanding of the types and shapes and kind of rationale behind the formation of our molecular orbitals, then we're going to get into drawing some molecular orbital diagrams. And then next week, we will be able to take information that's given to us from those molecular orbital diagrams to get a full portraiture of what's going on in the bonding in some kind of chemical compound.